So hello everyone, welcome back to Hasvora Education. This is a revision guide to the physics practical that is going to be conducted on 22 of May 2025. This guide contains some key points and tips plus the important scenarios that you need to keep an eye during the practical. It contains the that how you have to maintain the significant figures and the possible limitations and improvements that you can add in your question number 2 of the practical, and also how to write your answer so that you get full marks in it. So coming to the first and the foremost topic of this, which is how to choose the significant figures and the decimal places when you are recording your measurements. So you have to record the measurements and the reading to the precision of the measuring instrument. For example, if you are using a scale, it has a least count of zero point 0.1. For example, it can give you a reading to 2.9, 2.1, for example, 2.9, 2.1. So when you are using any instrument, you have to record the reading to its precision. For example, if you are then using a stopwatch, it normally gives you two decimal places, so you have to record the reading to two decimal places. For example, 1.23 seconds, 12.31 seconds. And when you are using a voltmeter, it usually gives you 3 to 3 decimal places. It gives you the value, so you have to record like 2.371, 1.607 volt. But look for the preciseness of the instrument, look for the least count, as some voltmeter also give to 0.01 or 2 decimal places. So in that scenario it will become 2.31 volt. So you have to record the individual readings, like the ones which he had asked individually, to the precision. And if you see examiner awarding 2 marks for a single reading, then most probably he needs multiple readings and the average of that value. Like in the case of measuring the time period of oscillation, you have to take two uh, two times you have to take 2 times the 10 oscillations, and then you have to take the average of that 10 times oscillation, and after that you have to divide it by 10 to get the time period. But it involves taking two values of t and then dividing by 10 to actually taking the average, and then you are going to take the time period. So that is why the examiner actually awards you another mark that is actually for the average. So you are going to be looking for it. Record your values as it is in the table. For example, if it is question 1, and then maintain the decimal places. But if you are calculating any value from that readings, keep the significant figure same. I have also drawn uh, an ideal table here, which you should draw like this. Just let me show it to you. This is the ideal table I have drawn. You have to just ethically add the serial number to show the values that you have recorded, and you are always going to be the recording the first values, like the x centimeter, which is going to be the independent variable, or which you are actually you are changing that. So you have to be you have to be representing that in an ascending order, like from the smallest to the largest. And then you like, for example, in this case I have picked a scenario in which x was a distance from the bench to the pendulum, and it was actually the not from the pendulum, it was actually a height at which a rod was placed to the pendulum, so that it was used for varying the speed of the oscillation. So as the distance was less, the the time period was also less, as it was oscillating very fast. It was coming in contact with the rod, and then it was oscillating. And when the distance was greater, the time was more. So this is how I have recorded the values, You can clearly see that I have recorded to two significant figures as my watch gave me to the value to two decimal places, while for the scale it gave me to the zero point 0.1 accuracy. So that's why I have taken to 20.0, or it can be 13.2 and anything like that. But you have to maintain the preciseness. And for the time period, you can see the time I have taken to two decimal places at the stopwatch mostly gives to two decimal places, while after calculating the average, you can see T1 plus T2 divided by 2. I told you when you are going to calculate, you are going to maintain the significant figures. Then first you are going to maintain the decimal places, but when you calculate something from it, you are going to maintain the significant figures. So you can see that both are of say significant figures. Then I have added another uh, column to it, which is the 1 over time period. I have not added the unit by mistake. It is going to be s minus 1. It is going to be s minus 1. So you are going to be also recording it to three significant figures. So decimal places is checked and maintained when you are adding or subtracting, or you are just you can say you are just taking the reading, and the significant figures are maintained where you are calculating something from that reading. So this for the question one. Now the important error and limitations and the improve in their improvements, which are usually of vital importance in the question number two. So the one of the mostly used, and it can apply in every scenario, and you can write it in each scenario, is the error of the two readings of k. Mostly they require you to calculate a value of k in the last, and then you can actually write that the two readings of the k are not enough to draw a valid conclusion, because it actually increases the uncertainty. You are just calculating two values of k from different values, so it is not like not a concrete proof. So the improvement can be take more reading with different mass or length, any quantities which are used in your scenario to calculate the k. So you have to be differing that to calculate the values and the readings, and you have to calculate more values of k to draw a graph. So this is the error and the improvement that can be applied to any of the scenario. The others are divided into the oscillation scenario, the terminal velocities of the cone. So let's check them out. So the oscillation scenario, the first error that can be experienced is the difficulty to judge the start and end of the swing. Like you just release the bob and then it oscillates, but you do not know from which point did you release it, or to which point when it comes you have to count it as a one oscillation. So what you can do, you can use a fiducial marker to mark the start and end. For example, it can be a line or something. You can say it could be fiducial marker is more like of, you can say, a representation. Like you can also place a rod at that point and you can just release it from that point. So this is the improvement of this error. The other error that can be experienced is the time of the oscillation is small and adds a greater uncertainty in value of t. Why it adds this uncertainty is because of the human reaction time, which is zero point 0.1 second, but you have to just overestimate it to be zero point 0.2 or zero point 0.3 seconds. So what you can do, you can take more number of oscillation. What will it will do, it will just spread the error, the uncertainty in all the values. Or what you can do to reduce the reaction time and the uncertainty, what you can do is you can connect a motion sensor, connect to a data logger. So what it will do that whenever the one of the oscillation is completed, it will automatically stop the timer and calculate the time. So there is no human reaction time or uncertainty involved. The fourth error that can be experienced in the scenario is the oscillations are not restricted to one plane, and obviously you have to you must have it experienced one or more time in the lab. Whenever you are swinging the bob, it not only moves in in one direction, but it also moves to the left and the right, which will definitely cause some of the error in your results. So what you can use is the use of the parallel guides to restrict the oscillation in one plane. Parallel guides are like, you can say, two you are specifying the path of the pendulum bob, that it moves within these two lines. It does not move to the left or to the right. So the other scenario is the terminal velocity of the cone. Like you are dropping a cone from a height, and then you are measuring the time at which it comes to the terminal velocity. So what can be the errors in this? The cone does not fall vertically downwards. For example, it can fall at an angle. So what can be what can be its um, improvement? Its improvement can be the same as the use of the parallel guides to restrict its motion. For example, to ensure that it moves vertically, or you can also use two clamped rulers so that you can ensure that it falls between them as a vertical path. The other error is the difficult to determine the height from which the cone is released, as the scale can't be kept vertical. For example, if you are holding the scale and the cone at the same time, your hands will probably wobble and you would not be able to keep the scale vertical. So you can use a clamped ruler and take the reading at the eye level to the scale to avoid balance error. The seventh error that can be experienced is the cone diameter may vary as it squeezes when measuring diameter. So in this scenario, what this examiner actually asked was also to calculate the diameter of the cone. So the cone was made up of the paper. So that's why when actually we were measuring the diameter, the cone was squeezing and it was varying the diameter. So what you can do is you can use a cone made from X-ray sheet or a hard material so that it don't squeeze. What else can be done is that you can take the diameter horizontally and vertically, and then take the average. The 8 point is not enough height for the cone to reach terminal velocity. For example, more of the scales that are provided to you are of 100 centimeter. Okay, but it will not necessarily be uh, effective for it to reach terminal velocity. So what you can do, you can increase the height from which the cone is released to allow it to reach terminal velocity. The ninth point is difficulty determining when the cone strikes the surface. So you have to actually stop the timer when it strikes the surface. So you can use a pressure sensor connected to a timer to stop the timer as the cone hits the surface. The another scenario that was actually that can be actually asked is temperature change using the resistor. For example, you are submerging a resistor in some water, and then this resistor gives off some heat, and then you are measuring that heat that is being dissipated in the water. So the resistor is not fully submerged in water. This can be one of the error, as some of the heat, not all the heat can be transferred. So what you can do is that you can increase the volume of the water to ensure that the resistor is fully submerged. The other point that can be valid is change in temperature has very small range, so which adds the greater uncertainty to the value of the delta change. So the the experiment that actually we conducted, the temperature change was actually 2 or 3 degree. So what is the least count of the temperature of the thermometer? So it gives you value to 0.5 degree, and you are actually calculating two times. So it is multiplied by 0.5. It gives you an uncertainty of 1 degree. So in a small range of 3 degree change, 1 degree is more of like a 25% of uncertainty. So what you can use higher voltage to cause more change in the temperature, so that to reduce uncertainty, What else you can do is you can use a more precise with small graduation, or you can use an electronic thermometer so that you can increase the precision and reduce the uncertainty. So the number 12 point is some of the heat is lost to the surroundings. So what you can use of insulation. The glass wool insulation is most effective in preventing the heat loss, and you can also place a lid so the heat is not lost to the surroundings. Number 13 point says some of the water sticks to the cylinder when the water has been transferred to the beaker. So in this scenario, we were asked to transfer the water from the cylinder to the beaker. Uh, so what actually happened was some of the water molecules actually stick to the cylinder, and not all the mass was being transferred. And actually, they also required us to calculate the mass of the water. So so there will be uncertainty, and there will be some error because some of the water remains and not all the water has been used. So what we can do is that we can calculate the mass of the water before and after to ensure that all the water has been transferred. So it was an electricity question in which we were being tested to calculate temperature change using the resistor. The other error that was being seen here was the contacts were being dirty. Some of them the mesh were being spread out. So what we can do with it was to we can clean it with the iron wool so that it does not cause problem in connect in making the connections. The other limitations, which are non-specific and can be used according to where it is valid, is the distance has a smaller range, which adds greater uncertainty to the value of x or any of the distance variable that have been given to you. For example, in it can be any you can say a distance, or it can be a height, or you can say a distance between 2 points, which has a very small range. For example, you can say 5 centimeter. So the uncertainty is greater when you are actually calculating a smaller height, or you can say a smaller distance. So what you can say is that you can use a micrometer if, for example, it is less than 2.5 centimeter. For example, sometimes it they are asking you to calculate the diameter of a ball, of a small ball. So what you can do is that you can use a micrometer or a vernier caliper to reduce the uncertainty, because it has high precision, it has small graduations, so you can calculate it very precisely. Another valid point is the difficult to determine the center of the ball. Like I mentioned earlier, that they often ask you to calculate the center of the ball. So it is difficult to assume the center in some cases, because the ball is mostly not uniform and not in its geometric shape. Like it is made up of, you can say, of a dough, or something, a material like that. So it is not a perfect ball. So what you can do is you can measure the diameter vertically and horizontally. The center of mass will be the intersection of the both lines. 16 point says the component has grooves and is not completely a cylinder, so the volume is inaccurate. So this applied to the scenario of the capacitor. For example, we were being asked to calculate the volume of the capacitor by just applying the volume formula of the cylinder. So it was not actually a perfect cylinder. So what we could say was that use the displacement method. By dropping the component into the water, the volume of the water displaced is the volume of the component, because it contained some of the grooves which did not make it a perfect cylinder, and it will also affect the charge stored in the capacitor. The other point is the Newton meter is difficult to be maintained vertically. We were measuring a force, and we were suspending it from the Newton meter while still holding both of the things together. So what we could do is we could use a set square and clamp to ensure the Newton meter is vertical and perpendicular to the surface. Another point is the difficulty to measure the the maximum height the ball reach after rebound. In this was a scenario in which we were dropping a ball and we were measuring the height at which it reaches after rebounding from the surface. So it was it had a most of the error because it is difficult to measure the height of a ball that is actively being like in the air. So what we could do is that we could use a scale placed behind the track, like on the track uh, on which the ball is dropped, and then we could use a video recording to like record the video of the ball as it rebounds and reaches the maximum height. We could watch it frame by frame to calculate the height as the scale is being placed behind it. So you could pause the video, watch it frame by frame, and then observe it. Other point is hard to release the bob without applying uh, applying some force. This was also the error in that same scenario in which where we were dropping the ball. So what we could do is that we could use a card gate or an automatic clamp which could automatically release the ball as we send the signals. The other point is it is difficult to judge when the water level reaches point P. So this applied to the scenario where we were actually we were there was some water in a beaker was given to us, and we were just measuring the pressure by making a hole in that beaker. So the water was actually coming out of that hole, and we were being told to stop the timer when the water level reaches the P. So actually it was very difficult to judge because the water was also transparent and the beaker was also transparent. So it was a bit you can say difficult to see when it reaches the point P. So what we could do is that we could dye the water so that we could easily keep an eye on the water level as it reaches B. Uh, the other point that was in the same scenario was the labels were being rubbed off due to being in the contact with the water. So we could use a permanent marker to make the labels. The third and the last point that you have to keep an eye is the possible answer to justify the significant figures and your relationship. The examiner oftenly asks you to justify the significant figures you have used and about the relationship, whether it is being supported by the results of yours or not. So the first one that I have written for the significant figures is that since I have taken my value of mass and length can be, it is just an example, okay? It is the dependent values used to calculate the value for which the justification is needed. For example, if I calculated K from the mass and length, or it can be density, which I calculated from mass and length. So I would say that I have taken my values of mass and length to 2 and 3 significant figure respectively. So I rounded off my value of K, or you can say density, to nearest 2 significant figure, which is the least number of significant figure used, because we round off to our values to the least number of significant figures, or from which the least number of significant figures of the dependent values from which it is calculated. The other valid point that can be is since I have taken my value of A and B to 2 and 3 significant figures respectively, I rounded off my value of K to 3 significant figure to maintain and preserve difference. Now this can be applicable in the scenario, for example, if there is very small range in your values, for example k1 and k2 is 1.47, 1.5, 1.41. So in this scenario, if for example we just round off to the near to the to the least number of significant figures, it will become 1.5 and 1.4. So the difference, maintaining the difference is important in values like this. So this could also be a possible answer. The third one is about the relationship proving. For example, they give you an estimated percentage uncertainty, and then they ask you that whether your percentage difference in the value of k is supporting the result or not. So you have to provide a structured answer to this, and the answer is the percentage difference in my value of k is, then you have to provide the red highlighted area is actually your percentage uncertainty, which is less than the estimated percentage uncertainty in experiment, which is mostly given to you in the question. Thus, my results support the relationship under under the given experimental accuracy. So this is a structured answer to the question of the uh, relationship proving. So this was for all for today. I hope you are well prepared for your practical paper of paper 34 on 22 of May. We are all hoping for the best. I meet you in another informative video. Till then, goodbye.